We're now going to consider another integral of a linear function, namely minus x over 2 plus 4. I've graphed that function right here, but this time instead of integrating out to some specific number like 2 or 3, we're just going to integrate out to some generic spot along the x-axis. Let's call it t. So in other words, what is this function f of t? Well, it's the integral from 0 to t of the function minus x over 2 plus 4. In other words, the function f of t tells you how much area has been accumulated if you integrate out to the number t. So now you should think about this t as some parameter. This is again some variable that you can move. So think about sliding t to the left or to the right. As you slide t back and forth, this vertical line, that's going to move back and forth, and you're going to be accumulating different amounts of area. That's what the function capital F of t is doing. It's telling you how much area you've accumulated out to the spot t. Let's find a formula for this function. In order to do that, we're going to use our old tricks. We don't need Riemann sums or anything because this can be determined just using boxes and triangles. So if we split up that region like that, we have a box and we have a triangle. What's the height of that box? Well, the height of that box is determined by the y value on the graph at the input x variable t. By definition, that's just what you get if you plug in t as your input x into the function. So in other words, that y variable right there, that y value, is minus t over 2 plus 4. That means that the height of the box is given by the product of minus t over 2 plus 4 times the width of the box, which is t. So let's write that all down. We're going to compute this area as the area of the box plus the area of the triangle. Sounds good. And then what was the area of the box? I just said it out loud. I'll say it again. This box has width t and height given by this y variable minus t over 2 plus 4. So the product of those two dimensions is that product right there. That's the area of the box. That's the width times the height of the box. What about the area of the triangle? Well, the height of the triangle is what's left from this y-intercept 4 after you subtract off minus t over 2 plus 4, right? And so in other words, that little bit of y-axis, how much is there, is exactly t over 2. All right, t over 2 is the height of that triangle. What's the width of the triangle? Well, it's t again, right? It has the same base as the width of the box, but then we need to divide by 2 because it's the area of a triangle. So that's height times base divided by 2. That'll give you the area of the triangle. And this is fantastic. Just from the geometry, we have this formula for the area accumulation function. If I plug in a t value, this formula will tell me how much area there is under the curve. We just need to simplify, okay? I'm going to do this in my head. Maybe, if you're working through this at home, it would be a good idea to check the steps. There's going to be a minus t squared over 2. What happens over here? Again, there's a t squared over 2, but we divide by 2 again, so that's a plus t squared over 4. So if we have minus t squared over 2 plus t squared over 4, we'll end up with minus t squared over 4. And the only other term is the 4, which multiplies by the t to give 4t. So this area accumulation function in this case is given by minus t squared over 4 plus 4t. Alright, and now here's a cool thing. That argument, it was dependent on the t variable being here to the left of this spot 8. Right? If I move t back and forth, that same argument will work for this region. What happens if t is over here larger than 8? Let's do that next. Okay, so now we're going to accumulate area all the way out to t, but t is bigger than 8. That means we're going to be getting positive area from this big triangle, but negative area from this little triangle because it's underneath the x-axis. Let's compute the integral. Here we go. So again, we're integrating minus x over 2 plus 4 from 0 to t to figure out how much area there is. And this time, it's given by the area of the first triangle minus the area of the second triangle, because the area of that second triangle that's underneath the x-axis. Okay. All right. What's the area of the first triangle? Its base is 8, its height is 4. Nothing complicated. So we have 4 times 8 divided by 2. That's the area of the first triangle. What about the area of the second triangle? Well, its base is the distance from 8 to t. So that's given by t minus 8. That'll be the base of that second triangle. What about the height of that second triangle? We're going to think about that height in the negative direction, right? It's below the x-axis. So we're going to go down by this amount. What's this y value? Well, it's precisely the output of the function, again, when you plug in t. It's minus t over 2 plus 4. And here's a nifty little fact. That's base times height divided by 2, giving us the area of the triangle. But check it out. If you plug in a t value that's bigger than 8, then that term in parentheses there that I just wrote down, minus t over 2 plus 4, that will be negative automatically. If you just think that through, that term is negative when t is larger than 8. That means that this formula automatically builds in for us this minus sign. Because we're using the output of the function in the negative direction, our formula automatically accounts for the fact that this triangle counts with negative area. So remember, when we integrate, everything above the x-axis counts as positive, everything below the x-axis counts as negative. Now, if you do the algebra out, it takes a little bit more work. I encourage you to do it on some scratch paper. Here's a cool fact. You end up getting the exact same formula that we got before, minus t squared over 4 plus 4t. So again, that will be the area accumulation function even when t is to the right of 8. What have we seen so far? We've computed that if we accumulate area under the function minus x over 2 plus 4 from 0 out to some parameter t, then we get this function minus t squared over 4 plus 4t. That always tells you the area under the curve if you go out to the spot t. Let's take the derivative of this new function, capital F, just for fun. So in other words, we're measuring the instantaneous rate of change of area accumulation. Well, what's the derivative of this piece? We have a t squared, right? So we need to bring the 2 down using the power rule, and then we subtract 1 from 2. That leaves an exponent of just t. So that's the derivative of minus t squared over 4. What's the derivative of 4t? That's just the constant 4. Okay? And now canceling the 2's, we see that we get minus t over 2 plus 4. That's the derivative of capital F. That's the instantaneous rate of change of the area accumulation function. Does that function look familiar? Check it out. You've seen that function before. It's right there, right? Those are the same function. I'm using different variable names because I didn't want to confuse things by integrating out to x, but the name of the variable doesn't matter. Would a rose by any other name smell as sweet? These are the same function. So this is really, really, really something special. We've uncovered some amazing pattern in the universe. The instantaneous rate of change of area accumulation is the function that you were accumulating area underneath. Okay, so that's sort of a mouthful. We're going to be unpacking that idea very carefully. All right, let's say it in a different way. If you start with the original function f of x, and then you accumulate area by integrating, let me just intuitively say that by integrating f, and this time I'm going to use the variable name x to make the pattern clear. So don't worry, you're integrating f of x, but let's just use x as the name of the variable that you're integrating out to. Then that area accumulation function will be minus x squared over 4 plus 4x. And what we've seen is that if you go and take the derivative of this function, you're exactly doing the inverse operation, taking the derivative brings you back to the original function. So integrating, taking area, and taking the derivative, they're inverse operations. They undo each other. Very, very, very cool fact. So the moral of our calculation here is the following. Integrating and taking the derivative are, in some sense, inverse operations. Now that's the content of the fundamental theorem of calculus. That's what we're working up to. I'm slowly introducing the ideas involved through examples. So before we get to actually stating the fundamental theorem of calculus here, I just want to formalize one idea that we've seen, which is this idea of undoing the derivative. Okay, we can talk about that without even talking about area. Check it out. If capital F of x is a function that satisfies the following equation, this equation just says that the derivative of capital F of x is the original function f of x. If you found such a function capital F, then we say that that function capital F is an antiderivative. That's the word, antiderivative of the original function f of x. So I'm just giving us a name for that idea. And we've already found one example. We found it by doing area accumulation. So we saw that if lowercase f is the function minus x over 2 plus 4, then the function capital F, given by minus x squared over 4 plus 4x, is an antiderivative of that original function. And there's an interesting fact here. There's many different antiderivatives, actually. You might think there's only one way to undo the derivative. There's many different antiderivatives, but they're all the same up to a constant. So if I tack on some constant to this capital F, I'll get another antiderivative. Check it out. If I added, say, 3, then what happens when I take the derivative of this new function, capital F? Well, I'd bring down the 2, it would cancel with the 4, I would get minus x over 2 plus 4, that's this, but then the derivative of 3 is 0. So this is also an antiderivative of this same function. Very cool. And they all have this form. The general formula for an antiderivative will be minus x squared over 4 plus 4x, and then you add some constant c. It's traditional in calculus to just write plus c when you write an antiderivative. That's just a reminder that all of the antiderivatives are the same up to adding on this new constant.
Give me your ring. I will return it to you when you find these things to be true.
Before we finally get to the fundamental theorem of calculus, I want to do one more motivating example. Suppose that I walk at 2 meters per second for 40 seconds. I stop then and I turn around and I walk at 3 meters per second in the reverse direction for 10 seconds. What is my total displacement? That just means how far is it from my initial starting point to where I ended up. And then we can also ask, what is my total distance traveled? That means how far did I walk? If I look at my Fitbit, that'll be like, the total distance, not taking into account which direction I went. So this schematic kind of shows what's going on. From 0 to 40 seconds, I'm going 2 meters per second to the right. I turn around and I walk at 3 meters per second for another 10 seconds, ending at t equals 50. So here's what we're going to do. we're going to graph the situation, but we're not going to graph the position function. We're going to graph the velocity function. Check it out. Okay, I've just graphed the velocity of my walking as a function of time. Over the first 40 seconds, I'm going in the forward direction at 2 meters per second, and then the last 10 seconds, I'm going 3 meters per second in the reverse direction, which means that my velocity is negative if it's going in the reverse direction. And now let's first ask, how far did I go just in the first 40 seconds? Let's not worry about those last 10 seconds. How far did I go in the first 40 seconds? Well, my rate of change is 2 meters per second, and it took me 40 seconds to go that distance. So over 40 seconds at 2 meters per second, I'll get 2 times 40. That's 80 total meters. And here's the crucial moment. Notice that 80 is exactly the area of this rectangle, right? The base is 40, and the height is 2. 2 times 40 is the area of that rectangle. So in other words, if we integrate the velocity function from 0 to 40, that's just the area under the curve, that's going to be the width, 40 times 2, and we get 80 total meters. So the integral is telling us exactly how far we've traveled from t equals 4 to t equals 40. So this is the distance traveled. 80 meters is the distance traveled from t equals 0 to t equals 40. I'm going at 2 meters per second, but it took 40 seconds to do so. So it multiplies. Okay, but now what happens in the last 10 seconds? We can also think about that in terms of area, but it's got to count as negative area. This is why the integral uses the area under the x-axis as negative. Because think about it, in those last 10 seconds, I'm going at 3 meters per second, right? So over 10 seconds at 3 meters per second, I'll go 3 times 10, that's 30 total meters, but I'm going 30 meters in the reverse direction, right? So that exactly corresponds to the integral from 40 to 50. If I integrate the velocity function from 40 to 50, I'll get negative 3 times 10, because it's width 10, 3 down, but in the negative direction, negative area. I'll get minus 30 meters, right? So that corresponds to going 30 meters in the reverse direction over those 10 seconds. Okay, so now we're ready to answer the original questions. First of all, what's the total displacement? The total displacement means what's the distance from my initial position to my final position. That will be given by the integral of the velocity function from 0 to 50. And now we can split up integrals along the integrating numbers, right? Integrating from 0 to 50, I can split that up as the integral from 0 to 40 and then the integral from 40 to 50. And we just computed each of those integrals. They were 80 and minus 30. So if I do that subtraction, I'll see that 50 meters is the answer. So in other words, if I look at, let's go back to the schematic, if this is my initial position, I move forward and then back, this total displacement is going to be 50 meters. Okay, what about the total distance traveled? That's a little different. When we think about the total distance traveled, we don't really care if we're going to the right or to the left. That's just our overall, how far we walked. That's going to be given by the total area of the boxes, regardless of whether they're above or below the x-axis. So it's going to be given by the integral of the absolute value function. That just means that these 30 meters that we walked backwards we're just going to count them up as meters. We don't care if they're forwards or backwards. The total distance I've traveled, the total distance I walked, is 80 plus 30. That's 110 meters.
E.J. Cooper loves coffee.
Okay, what have we seen in this example? We started with a velocity function. It was super simple. It was this piecewise function, 2 and minus 3. Those were our two different speeds when we walked. And then we saw that integrating, accumulating the area, exactly gave us our total displacement. So the integral of velocity is going to give you the change in position. That's what I mean by displacement. By displacement, I just mean change in position. Okay, so if p is the position function, then what I'm saying is that integrating velocity gives us the difference between p of b and p of a. Let me notate here. That's my initial position at time a. In the example, it was time 0. And here, that's my final position. So it's giving us the distance between my initial position and my final position. That's what integrating does to velocity. But we already know the relationship between velocity and position. We saw earlier in the course that if you take the position function, the position that you're at as a function of time, and then you take the derivative with respect to time, the instantaneous rate of change of position, that's a t there, I'm thinking position as a function of time, then the derivative of position, essentially by definition, is velocity. So we see again that we have another example of how integration is inverse to taking the derivative. Integrating velocity gives us the change in position, but taking the derivative of position gives us velocity. This is really the same phenomenon that we saw in the previous example. The derivative and the integral are inverse operations. They undo each other. We're ready to state the fundamental theorem of calculus. Hallelujah. Hallelujah. But it turns out that there's actually two parts to the fundamental theorem of calculus. This is only part 1, so stay tuned for part 2. The first part of the fundamental theorem of calculus says Hallelujah. Hallelujah. That if we take a continuous function f of x, and then we look at the area accumulation function, starting at some x value a, and then accumulating area all the way out to some other x value t, and keeping track of that integration from a to t as a function of t, let's call it capital F of t, then this function, capital F, its instantaneous rate of change is the original function f. In other words, using the variable name x, f prime of x is f of x. That's what the fundamental theorem of calculus, part 1, says. We can restate this using the language of antiderivatives. In other words, integrating from a to t is an antiderivative of f of t. Here I'm thinking of it as a function of t, so I'm using t as the input variable for little f, but that's not important. Don't worry about that. It's just the name of the variable. The point is that this function gives us a ready-made by hand antiderivative of the original function. Different values of a, what would be different values of a? That's just like different starting points, right? As you change t, that behavior of area accumulation is all going to be the same. The point is that different starting points means that your initial area accumulation kind of at the beginning might be different. So these will all be different antiderivatives, but they'll all just differ by a constant. They're all the same up to a constant. All right, that's the fundamental theorem of calculus, part 1.